Hello and welcome to this next lecture on fundamentals of acoustics. We are looking at measures of sound, and we have presented sound pressure level, sound intensity level and sound power level, and we are now looking at relating the reference values if we take the measurement in the far field. Okay. So now so here is my sound pressure level LP, this is my sound intensity level LI, and P reference I have said is 20 micropascals. 20 micropascals. Okay. So now if we work with Li, which is 10 log to the base 10 P square RMS, and I do a P square reference and a P square reference by rho C I reference. Okay. Then if I separate them out, 10 log to the base 10 P square RMS by P square reference plus 10 log to the base 10 400 into 10 to the power minus 12 by rho C for air, rho into C for air is approximately 415, somewhere in that range. It varies with temperature, humidity, etc., but somewhere in that range. Then into I reference. Okay. So now if we take 400 to be close to 415 and I reference to be 10 to the power minus 12, okay, then what I have is I reference is equal to 10 to the power minus 12, then this 10 to the power minus 12 cancels, this approximately cancels, so that I have 10 log to the base 10 of 1 approximately, which is 0. And this what we have from here is LP. So if we are measuring in the far field, okay, the reference values are taken such that LP is equal to Li. Okay, and this is a big jump in convenience, because earlier intensity we said requires 2 microphones. You have to measure pressure, you have to measure velocity, velocity is the gradient, etc., etc. But the way we have arranged the reference values, LP, which is taken with a single microphone, is equal to Li. Okay. So once you have your LP which is equal to Li, you can get your intensity level, as before. Let's say in one grid, okay, you have intensity level in raw value in watts per meter square, and let's say this area is A, so that intensity level that you measure in linear values into A is the power out of the area, power out of that area. Okay. So from a single measurement, single point measurement, you have power, okay, which is an area measure. And if you have many grid points around the source, then you have I into AI is Wi from each of these areas. Then you sum up the power from the areas, you have the total power. Okay. So now how does it work? So we have a source. Okay, we have a source that is making sound. Let's say we put a grid around the machine. We put a grid around the machine. So here's the grid. Okay, grid of wires. So similarly in the other direction, so we enclose it completely. It's completely enclosed from top through these wire meshes. Okay, and we are in the far field, let's say. Then you go and take a measurement at a point, you get an LP at the ith location. Okay, then that itself I take as the Li at the ith location. Okay, that means what? 10 log to the base 10 I by I reference is equal to Li at the ith grid point. This is the ith grid point, let's say. Okay, then log to the base 10 raw intensity by intensity or reference is Lii by 10. If I now take this and paste it here. Okay. So now what do I have? To convert this to linear units, I linear intensity units of the ith grid by I reference, which is 10 to the power minus 12 watts per meter square, is 10 to the power Li at the ith location by 10. Okay. Then the intensity at the ith location in watts per meter square is I reference into 10 to the power Lii by 10. Okay. So now this intensity in watts per meter square I have for the ith grid, and let's say suppose I goes from 1 to 100. Okay, so I have measured intensity at 100 grid points, and let's say each grid point, each grid slight variations in area has an area Ai. Then in watts per meter square, the total intensity, total power, so then the total power as watts is the intensity from each of the grids in watts per meter square into the area in meter square. Okay, this is equal to the wattage from each area, and then total W total is summation of this from all the grid points that are covering the machine. Okay, then finally the LW sound power level is 10 log to the base 10 W total by W reference. W reference is 10 to the power minus 12 watts. Okay, Now let's see here. So one thing of course is when we have sound pressure level and we have sound intensity level, why go for power level? Why power level? Okay, that's pretty simple because sound sources are directional. Okay, so if I have a source here, it could be radiating more in this direction, very little in this direction, and some oblique angle more, and etc. etc. So if you go and measure over here or measure over here and you get some LP value or LI value, they are not indicative. Not indicative of the machine capability, okay, as a sound source. And so you need to go to LW. Okay. However, as a quick measure of how much sound a machine produces, you can have average SPL values, okay, averaged LP values. LP values. Okay, so you have a machine that is producing sound and you don't want to do this detailed gridding and etc. etc. So you measure LP1, LP2, LP3, LP4, okay, let's say a meter away or something like that based on an ISO standard. Then you can have an averaged LP value. You can convert this into linear values of P square RMS, sum all those up, okay, and then divide by 4 and you can have an averaged LP value. Okay, so that's as far as the YLW as a measure. Okay, now another thing is this method of using 2 microphone probes has a certain advantage, okay, has a certain advantage. What is that advantage? One is that we can measure in situ. That means where we are, where the machine is. Okay. So if we can be, let's say the machine is sitting somewhere, in a room, okay, and there is a neighboring machine. And that is making sound, and this is also making sound. Okay, this is also making sound. So now what do? If we want to find the power due to this machine, then we put a grid around it. We put this standard grid around it. Okay. and say we measure using our 2 intensity probe, 2 mic intensity probe. Why? Because we cannot be in the far field. Okay. Then the question arises, will the neighboring machine neighboring sound from the neighboring machine disturb the readings? Okay, will it disturb the readings? No, it won't disturb the reading. The reason is that if there is no other transient event, happening during the measurement, okay, the sound that is being made by the neighboring machine enters the grid and also exits the grid. Okay. So what happens is that if this machine is held steadily in its operation, okay, then when we are measuring on this side, okay, the intensity being a vector will point in this direction, whereas the intensity on the other side will point in that direction, okay, so that the power due to the neighboring machine which is outside the grid will cancel out. In one instance it will go in one instance it will go out. Whereas as far as the machine is concerned, at all the points, the normal points away from the machine, okay. As far as the outside machine is concerned, the normal points in one instance here towards the machine, in another instance away from the machine, so that the power due to the neighboring machine enters the grid and exits the grid, okay. But whereas with respect to the source that we are trying to measure, which is inside the grid, the normal always points away from the machine. So this we are always accounting for the sound power coming from the source, okay. So if there is no, suppose somebody opens the door suddenly and shuts the door during one measurement, that will pollute your measurement. But if this is steadily making a sound, it's steadily on the neighboring machine, and you have your machine that is making sound, if you use the 2 microphone intensity probe, okay, it will cancel out the effect of the neighboring machine, okay. However, if you don't like this, okay, you want all ideal situations, okay, then what you do is you bring, if this machine is transportable, you take it out of the situation from the industry and bring it to your own lab, where you have a anechoic chamber. Have an anechoic chamber, okay. What is an anechoic chamber? An anechoic chamber is one where the entire chamber, okay, entire chamber on its walls has non-reflecting wedges made of a certain foam, okay, foam wedges, okay, that absorb sound. Okay, even the ground is isolated, the whole room is isolated, whole room is isolated. Okay, so whole room is isolated from vibrations. Okay, if you want to make that sensitive, and the floor is actually a mesh, floor is actually a mesh, so you will be standing on a mesh, and beneath the mesh are these again acoustic absorbing foam that is placed beneath. Okay, so now if you place a source over here, okay, you will only measure outgoing sound. Okay, no reflections from the wall. Okay, so you don't have the disturbance from a neighboring machine. Okay, and you can be in the far field if you want, and you can get accurate measurements. Okay, now there is another version of this anechoic chamber, which is a semi-anechoic chamber, or it's called a hemi-anechoic chamber. Okay, what that is it's the ground is hard. Okay, the ground is hard, but the rest of the walls have these anechoic wedges, sound absorbing anechoic wedges they have. Okay, and this is typically used for reporting sound related to vehicles. Okay, you have a vehicular traffic and you have to assess what the vehicle is doing. Vehicle typically moves on the road, which is hard. Okay, road is hard, so this floor is hard, and then the surrounding goes to infinity. So if you have a road and you have a vehicle, okay, the surrounding is infinite. Okay, so now the floor is made hard and all the other 5 surfaces are absorbent, so it simulates the road environment. Okay, so these are different setups for measuring sound power of machines. Okay, now let's do a simple calculation here. Okay, let's do a simple calculation. So I have sound pressure levels at 4 points around a machine. This I am taking from a book by Professor M.L. Munjal. He has a book which is titled Noise and Vibration Control. Okay, from World Scientific. Okay, so we have a machine. Around the machine we have sound pressure levels, that means LPs at 4 points around the machine, same machine. Okay, when the machine is on, and the machine is on, the 4 values are 85 decibels, 88 decibels, 92 decibels and 86 decibels. Okay. Now the ambient level when the machine is off, okay, the ambient level of sound is uniformly 83 dB. Okay. So what is the average sound pressure level due to machine alone? Okay. So now we have LP. Okay. So if we get to the raw P square RMS, okay, so 85 dB, so 10 log to the base 10, let's say P square RMS location 1, P square reference is 85 dB. Okay, so P square RMS by P square reference is 10 to the power 85 by 10 at first location. Okay, so these are now raw numbers. So similarly, if I calculate P square RMS 2 by P square reference, P square RMS 3 by P square reference, P square RMS 4 by P square reference, okay, then I have addition of these plus 10 to the power 88 over 10 plus 10 to the power 92 by 10 plus 10 to the power 86 by 10. Okay, and I divide this by 4. This is the averaged value in linear units. Okay, then I take 10 log to the base 10 of this value, let me call it x. That turns out to be 88.6 dB. This is the averaged SPL when the machine is on. With ambient. with ambient levels. Okay. Now the machine alone, the machine alone so you take the raw value that comes from the machine alone, 10 to the power 88.6 by 10, okay, and subtract 10 to the power 82 over 10, okay. This is the raw p square RMS by p square reference. Now you take 10 log to the base 10 and that turns out to be 87.5 dB. Okay, this is the machine alone. Okay. In another example, suppose we are measuring sound at a single point. Okay, in a community location, okay, in a community. Somebody has complained that there is high sound level here throughout the day, something has to be done, maybe it's near a hospital. So we are measuring every hour we are going to measure, let's say for 8 hours at a same point, single point. Okay, so now we have 8 dB values. So what do? So we take the LP I running from 1 to 8. Okay, so the raw unit is 10 to the power LPI over 10. Okay, these are the raw p square RMS by p square reference values. You sum them up, okay, I going from 1 to 8, then you divide by 8. So now you have the average linear unit. This is the average p square RMS by p square reference. Then you take the 10 log to the base 10. Okay, so that gives you the average SPL over an 8-hour period. Okay. There is a lot more to be said. We will look at the frequency content, how to describe. Okay, this RMS value, that it collapses all the frequency content. You could have the same RMS value for a high frequency signal or for a low frequency signal. So that frequency information is washed out. So we will bring in how to now account for frequency content in the next few classes. Thank you.